Today we're moving into Chapter 5, and we're going to start in Section 5.1. Section 5.1 is about an introduction to normal distributions and the standard normal distribution. Okay, so let's think back to Chapter 4. In Chapter 4, we discussed discrete probability distributions. And remember, we had discrete and continuous, and discrete probability distributions were those that had a finite number of possible outcomes. Now we want to move on to the continuous probability distributions, which are the distributions that have an infinite number of possible outcomes. There are infinitely many different continuous probability distributions, but what we find out is that as we work with them, the most important one is called the normal distribution, because it can apply to so many different things. So we want to really focus in on this normal distribution. Now, if you go on to take a more advanced statistics class, if your major requires you to do that, then you'll take a more advanced statistics class and you'll discuss non-normal distributions. But in this class, we're going to stick with the normal ones. So let's talk about the normal distribution. The normal distribution is a continuous probability distribution for a random variable x. The graph is called the normal curve. We've actually seen the graph before. It's a bell curve. Okay? So in a normal distribution, there are several conditions. The first one is that the mean is equal to the median is equal to the mode. So if you remember back when we talked about the shape of a distribution, we saw that the mean was equal to the median was equal to the mode in symmetric distributions. And so the normal distribution is a symmetric distribution. The normal curve is bell-shaped, right? So it has a bell curve graph to it. If you remember when we talked about the empirical rule, we saw bell-shaped curves, and this is one of those curves. What else? Well, the normal curve is symmetric about the mean, right? We just mentioned that it was a symmetric distribution. And the total area under the normal curve is 1. You may remember when we were talking about the discrete distributions, we noticed that the areas of the bars when we made the histograms corresponded to that probability. And so this too will lend itself to probability as we start talking about the area under the curve. Our fifth point here is that the normal curve approaches but never touches the x-axis, right? It gets closer and closer and closer. On the tail ends, you see how it gets tiny, 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 and it looks like it touches that x-axis, but it never actually does. If you took a magnifying glass, you would see there was still a little bit of space there. And then lastly, the points of inflection, which are points where the curvature changes, occur at a distance of sigma units from the mean. So you can see where those inflection points are on the graph, and you'll notice that there's a change. As we go from left to right, you see how it's kind of swooping upward the curve is. And then once it hits that first inflection point on the left, it kind of starts to turn down. So on the left, it's turning up. It hits the inflection point, it starts turning down. And then when it hits the next inflection point, it starts turning up. That's what we mean by change of curvature. From curving down to curving up, or from curving up to curving down. And those inflection points happen at a distance of sigma, which is the standard deviation units, from the mean. Okay, so when you look at any one of these normal curves, the mean and the standard deviation completely determine what the normal curve will look like. Because, like we said, there's infinitely many of these. So we've got two normal curves on the screen. Both of them are bell-shaped curves. They have the same mean. But the taller one has a much smaller standard deviation. Do you remember why that would be true? The reason that it's true is that when we talk about the standard deviation and the empirical rule, remember the empirical rule said that 68% of all the data values occur within one standard deviation, 95% occur within two standard deviations, 99.7% of all the data values occur within three standard deviations. If the standard deviation is smaller, then that means there's more data closer together. For more data to be closer together, it has to squish the curve in towards the center. And because the area under the curve has to be 1, if you push it in on the sides, it has to grow upward. So the skinny one has the smaller standard deviation because all the data has been packed more closely to the mean. And the wider one has its data farther away from the mean. Okay? So standard deviation always relates the spread of the data. If there's less spread, if the data is closer to the mean, then that means there's going to be a smaller standard deviation. So we have our first example. We want to look at a graph and estimate the mean and the standard deviation. Now, this is not an exact kind of a question. We're trying to build an estimate. So, the first thing that we can find is the mean. That's not hard, right? The mean is going to be right in the middle because these normal distributions are symmetric, and the mean is equal to the median is equal to the mode is right in the middle. So if we were to think of what x value is right in the middle, it looks like it's going to be 3.7. Okay, so I'm going to drop a little line in there so that you can see the symmetry in this curve. The next question about the standard deviation is a little bit harder. So we're trying to find points of inflection. This is by looking, so we're not using any kind of formal math here. If we look at the screen and we see this is curving upward here on the left-hand side, and then over here it's curving downward. So somewhere in here is a point where it changes. Same thing on the other side. Here we're curving downward, and then here we're curving upward. So somewhere over here there's got to be a change in the curvature. So I'm just going to estimate where those would be. And I'm going to say they'd be right around here. Okay? That seems pretty good. Maybe you could make an argument it's a little farther down this way and a little farther down that way. Again, this is not an exact process here. We're just trying to estimate the standard deviation. So if I took these points and I dropped lines just like I did with the mean, we get that. So we said the standard deviation is the distance between the mean and the inflection point. We're talking about the horizontal distance here. So that horizontal distance, in this case, the distance from 3.7 to 4.1, or the distance from 3.3 to 3.7, is 0.4. So that would be our estimate for the standard deviation. We would say that the mean is 3.7 and that the standard deviation is 0.4. Okay, so we got a little practice problem for you. We're going to do the same kind of a problem. You want to estimate the mean and the standard deviation for this bell curve. You're going to look for the mean, figure out where that would be, then try to decide for yourself where the inflection point should be. And when you're finding that inflection point, if your answer is slightly different from mine, that's because this is an estimate, and that's okay. So why don't you hit pause on the video, and when you're ready to come back, go ahead and hit play. Okay, so let's take a look at the solution. First thing we're going to do is identify the mean. It looks like it's right here in the middle. Halfway between 5.3 and 5.4 is 5.35. If you're struggling on why that is 5.35, if you look at the graph here at the bottom where we have the 5.3 and the 5.4, you could imagine putting a 0 at the end of each one. So it would be 530 and 540, and halfway between 530 and 540 would be 535. So that's one way that you can figure out the halfway point between decimals is by adding a 0 at the end of each decimal, and that helps you figure out where the middle is. Once we've got that decided, now we're going to turn our attention to the inflection point. We're looking for a curvature somewhere in here, right? We've got curving upward, and then we're curving downward, and it looks like it's changing right around here, and like right around here. So if I put those points in, I think that's a pretty good estimate. Yours might be a little farther left or a little farther to the right. If I drop down my vertical lines here, then I can see there's a distance. There's a distance between the mean and the inflection point. Distance between the mean and the inflection point. So, what is that distance? Well, we know that the point in the middle is 5.35. What about the point here on the left? What value would this have? And the answer is it's 5.25. And then this one on the right is 5.45. So the distance between 5.25 and 5.35 is going to be 0.10. So that would be my standard deviation. So we end up with a mean of 5.35 and a standard deviation of 0.10. Okay, so we can start to familiarize ourselves with these normal distributions, and once we've kind of got the idea of what a normal distribution is and how it works, we realize that even though they look different, some are skinny and tall, some are short and fat, they do all behave the same way. And since this is the case, we can totally standardize this process. And it generates something called the standard normal distribution. So there are infinitely many normal distributions, but we want to focus on the standard normal distribution. And then we're going to figure out how we can convert the values from any distribution, any normal distribution, to values in the standard normal distribution so that we only have to work with this one set of values. So let's talk about the standard normal distribution. Remember we said that the mean is mu and the standard deviation is sigma? Well, for the standard normal distribution, the mean is 0. So 0 is right in the middle of that curve. And the standard deviation is 1. So the inflection point happens 1 unit away from the mean. Okay. And again, the area under the curve is 1. So it looks something like this. Standard normal distribution. Funny thing is, we've actually talked about this before, and we didn't know we were talking about it. When we learned measures of position back in section 2.5, we talked about quartiles, percentiles, stuff like that, found the median. At the very end of that section, we learned something called the Z-score formula. I said it's really weird that we talk about it now because we don't mention it again till chapter 5. Well, guess what? We're in chapter 5 now. So here's our Z-score formula. The Z-score formula was x minus mu over sigma, where x is the data value, mu is the mean, and sigma is the standard deviation. Think about what this means. The top number, x minus mu, is the deviation of that data value x, right? Because we said when we were computing standard deviation, what we did is we found the deviations, taking each data value x minus the mean mu, and then we would work with that. Here we've got the deviation divided by the standard deviation. So that's telling me how many standard deviations away from the mean the x value is. How many standard deviations away from the mean the x value is. Okay, so the z-score for any data value is the number of standard deviations that separate that data value from the mean. For instance, a z-score of negative 1.23 means that the data value was located 1.23 standard deviations to the left of the mean. So one of the things that we really need to be good at is converting our data values, our x values, into z-scores. And so we're going to do a few examples of how to do that here. Actually, we'll do an example and then a practice problem. So, example. We want to find the z-score when x is 6.887, mu is 3.8, and sigma is 2.1. Okay. So all we're going to do is use this z-score formula. Z is equal to x minus mu over sigma. We're going to plug those numbers in where they belong. So the x is 6.887 and the mu is 3.8. And on the bottom of the fraction, we'll have the sigma, which is 2.1. When we subtract 6.887 minus 3.8, we get 3.087. So 3.087 divided by 2.1. And if you throw that into your handy-dandy calculator, you get 1.47. That's the z-score. So if we interpret that, that means that 6.887 is 1.47 standard deviations to the right of the mean. So we use the standard deviation as our measuring stick, and this is 1.47 of those away from the mean. So we got a little practice problem for you. Same kind of problem. We want you to find the z-score when x is 6.256, mu is 12.75, and sigma is 3.4. So hit pause on the video, and when you're all finished and ready to look, then hit play. Okay, so let's take a look at our solution. Again, using that same z-score formula, z equals x minus mu over sigma. The x is 6.256 and the mu is 12.75. So we get 6.256 minus 12.75 on top of the fraction. And on the bottom is our 3.4. We do our subtraction, 6.256 minus 12.75, and we get negative 6.494 over 3.4. If we divide, throw that into our handy-dandy calculadora, we're going to get negative 1.91. So again, if we interpret what this says, negative 1.91 means that the data value, 6.256, is 1.91 standard deviations to the left of the mean. We know it's to the left because the z-score is negative. So a lot of the things that we're going to do from this point forward are going to rely on our ability to calculate the area underneath the standard normal curve for various values of z. Because it's standardized, right, because we work with it so frequently, we've developed a table of values for certain z-scores that tell us the area, and it's called the standard normal table. Okay, so I've got a slide here that shows this standard normal table, and it's a big, ugly-looking monster table. Don't be scared by it. It's actually a really easy table to use. And we're going to look at some examples on how we use that table. First, though, we've got a note. See all these numbers in this standard normal distribution? Well, those numbers represent areas under the curve. You can see the two diagrams at the top on the left. It's showing you the shaded area underneath those curves. So, our note says that the standard normal distribution table contains areas under the standard normal curve to the left of the given z-score. So the values found in the standard normal distribution table represent areas to the left of the given z-score under the standard normal distribution curve. Standard normal table values always represent area to the left. Okay? So that's going to be important to us because sometimes we're going to have to calculate an area to the right, and we need to realize what that means we have to do with those table values. So let's look at an example. The first example is we want to find the shaded area under this curve using the indicated z-score. And our z-score is going to be 0.37. So because it's positive, it's to the right of 0. And we want to find that shaded area, the area on the left of that. Okay, so remember what we said. The area under this curve is equal to 1, right? Under any normal curve, the area is equal to 1. So if the area is equal to 1, we should already expect that the value of this area, the shaded area, is going to be more than a half, more than 0.5, because this represents more than half of the area under the curve, right? It's past the center. So that gives you a little rule of thumb to kind of help you figure things out, what you expect your answer to be. We expect our answer to be a little bit more than a half. So how do we use the table? Well, on the table, what you're going to do is you're going to try to find the row that's labeled 0.3 and the column that's labeled 0.7. Now, I know we're on a video lecture here, but you should still be printing out those notes to help fill in the blanks and keep track of everything. And on those notes, you should be able to look at that table. So if we look at the table and try to find that, the area on the table is 0.6443. And that's going to be that shaded area. Because this area that's shaded is to the left, the value from the table gives us area to the left. So the table value in this case is the area. The table value won't always be the area. So here's a practice problem. Find the shaded area under the curve using the z-score 2.29. So, if you want to hit pause and come back when you're ready, that'll be great. If you need to rewind the video so that you can see the table, that's fine too. And when you're all finished and ready to go, hit play, and I'll be here. Okay, so what we're going to do to solve this problem, we have to look for 2.2 in our rows. The rows are down the left side. And then we're looking for the column that's 0.09. So we always look for the first 2 digits of the z-score along the left-hand side of the table and the last digit across the top. So if we look for the row that's labeled 2.2 and the column labeled 0.09, then the table entry would be 0.9890. And because this is area to the left, that is, in fact, the area under the curve. Let's look at some negative z-scores. Find the shaded area under the curve using the indicated z-score, z equals negative 1.21. There's 2 pages of that table. The left-hand page on the slide was the negative for negative z-scores, and the right-hand page was for positive z-scores. So we're going to be looking at that left page. And again, kind of figure out what you're expecting ahead of time, right? This shaded area is less than a half, right? It's a pretty small little area. It looks like it's less than a quarter, right? So we're going to expect a pretty small answer when we're all done here. To solve this, we're going to look up the first 2 digits for the row. So negative 1.2. And then for the column, the last digit is the 1, but it's actually 0.01 because it's that second digit. And so if we look at negative 1.2 and the 0.01 where those meet, the table value is 0.1131. And because this shaded area represents area to the left, this is our area. So we've got a practice problem for you. Same idea, we're going to use a negative z-score. The z-score is negative 0.68. So go ahead and pause the video, and when you're ready, hit play. Okay, so for our solution, we're looking for negative 0.6 in the rows and 0.08 for the column. And we try to find the value where those meet. And that value is going to be 0.2483. And because this is area to the left and the table gives us areas to the left, this is our area. Okay. So it seems like all we're ever using is the table value for our area. But that's not actually the case. We're going to see a few problems now where that's not true. So let's look at this one. We want to find the shaded area under the curve using the indicated z-score. Z equals negative 0.41. This time, when you look at that curve, we're asking for area to the right. The shaded area is on the right-hand side of negative 0.41. So the table value always gives us area to the left. So we're going to have to do something a little bit different here. That shaded area, though, does represent more than half of what's underneath the standard normal curve, so we are expecting an answer that's bigger than 0.5. So how would we do this? Well, what's going to happen is we're still going to look up the negative 0.41 on the standard normal table. So we look for the row that's marked negative 0.4 and the column that's labeled 0.01. And the table entry that we find there is 0.3409. But that's area to the left. So this is actually the unshaded area. Right? That is the unshaded area. And remember that the whole area underneath the curve is 1. So if we took the whole area 1, and we subtract away the area on the left, 0.349, that's going to give us the area on the right. And that area is going to be 0.6591. Okay. So that's how we do area to the right. We find the area to the left and we subtract it from 1 because the total area under the curve is 1. And these shaded areas are really complements, right? You're either in one or you're in the other if you're under the curve. So we can subtract from 1. So try that yourselves in this practice problem. We want you to find the shaded area under the curve when z is 2.13. So if z is 2.13, you see that little tiny area in the right-hand tail. That's all we're looking for here. That's a really tiny area, so we're expecting something really, really small when we're done. So go ahead and pause the video, try to work this out, and when you're all finished, hit play. Okay, so if we're going to try to find this particular area, then what we're going to do is we're going to look up the row for 2.1 and the column for 0.03. And when we do that, the table value is 0.9834. That is the area to the left of the 2.13 on the graph. It's the unshaded part under the curve. We want the shaded part, but we know that all of the area under the curve is equal to 1. So if we took the 1 minus the 0.9834, then we would get our shaded area, the little tiny shaded tail, which would only be 0.016. So we knew it was going to be small because that's hardly any area at all, and 0.016 is pretty small. Now, what if we wanted to do something a little more advanced? Find the shaded area under the curve using the indicated z-scores. Notice it says scores this time. That means more than 1. So the first z-score is going to be negative 0.81. The second z-score is 1.86. And we're trying to find the shaded area between those two z-scores. The shaded area between those two z-scores. This one requires a little bit of extra thought. Okay? So, we're going to find each one of these z-scores. And so we find, I always go to the right, the one that's farthest right. So start with the 1.86, find that z-score, get a table value for that. Then find the table value for a z-score of negative 0.81 and get the table value for that. And if you take the difference between those, you're going to get the area in the middle. We'll see why that's true here in a second. So when you find the z-score for the 1.86, it gives you this area. You see my little blue arrow there. So everything from 1.86 all the way to the left. When I find the table value for the z-score of negative 0.81, it gives me this area. Okay? So if I take the bigger area and I subtract the smaller area, that's going to give me the area between. So we'll look up our farthest right z-score, which is 1.86. And the table value for 1.86 is 0.9686. Then I'm going to look up the z-score of negative 0.81. And the table value for that is going to be 0.2090. Then I'm supposed to subtract these. And what do I get when I subtract those? I get 0.7596. That's the area of the shaded region in the middle. Because to the left of 1.86 was an area of 0.9686, and to the left of the negative 0.81 was 0.2090 area, and the difference between those will be that shaded region. All right, so practice problem for you. Try to do something similar here. I want you to find the shaded area under the curve between these two z-scores. Z-score of negative 2.42 and a z-score of 1.94. If you look, that's most of the area underneath this standard normal distribution. So you're expecting a very high value, right? And remember, the value has to be somewhere between 0 and 1, so you're expecting a value very close to 1 when you do this. So go ahead and press pause on the video, and when you're ready to resume, just hit play. Okay, so we're going to do the same thing we did last time. We're going to start with the z-score that's farthest to the right, which is the 1.94. And then we're going to find the table value for that. We're then going to find the z-score of negative 2.42 and the table value for that. And the difference between those two table values will be the area in the middle. So I start with the 1.94. And the z-score of 1.94 gives me a table value of 0.9738. When the z-score is negative 2.42, the table value is 0.0078. So when I subtract those, I end up with 0.9660. Now remember, we said it was going to be big and that it had to be somewhere between 0 and 1. We were expecting something really close to 1. Well, 0.9660 is very close to 1. So that brings us to an end of section 5.1. Please remember to look on Pearson for your homework for this assignment, and have a great day.